For this video, we're going to look at lesson 3.3, intersection and union of two sets. And so by the end of this lesson, you should develop, generalize, and apply strategies for determining the elements in the complement, the intersection, or the union of sets. So for the couple examples that I'm going to talk about right now, we'll use the following sets to demonstrate the terminology. So we have set A, which is 1, 2, 3, 4, 5, and set B, which is 4, 5, 6, and 7. So if we're talking about an intersection, that is the set of elements that are common to two or more sets. And so we have A and the upside down U and B, so read the intersection of sets A and B. Sometimes you'll see the word intersection replaced with and, so this is A and B. And so if we say the intersection of A and B, and so that is the ones that fall into A and also fall into B, which are the numbers 4 and 5, as 4 and 5 are found in both sets. And so the other way I can put it, if I put an N out front, that's the number of the intersection of A and B. And so there's two things that fall in there. If I'm talking about a union, that's the proper facing U. And so this is the union of sets A and B. And so these are the ones that are found in A, but also in B. And so I'm including everything that's in A and everything that's included in B, but I only include it once. And so I'm going to write them from least to greatest, so 1, 2, 3, 4, 5, 6, and 7. And so if I want to do the number of A union B, then there is 7 things altogether. Now the last one here is A slash B. And so this is A minus B. And so what this is showing are the elements that are just found in A. So everything that's in A excluding what's found in B. And so if I look back at my sets that I started with, this 1, 2, 3, 4, 5 for A. If I want to do A minus B, I look over at B and go, okay, so the thing that they have in common is 4 and 5. So I'm going to exclude those. So I'm just looking at 1, 2, and 3 for A minus B. 1, 2, and 3. And so the numbers that are just in A, it's 1, 2, and 3, there's 3 of them. And so we've used this already, but we're going to put an actual name to it. So we have this principle of inclusion and exclusion. So the number of elements in the union of two sets is equal to the sum of the number of elements in each set minus the number of elements in both sets. Because what happens, if you include all of A and add together all of B, you've done this overlap twice. And so what you do to make it actually work is once you add all of A, you add all of B, and you minus the overlap because you've added it one too many times. And then what's left will give you what's actually there. So if we add 5, there's 5 in A, there's 4 in B, and we minus the 2 that's in the middle, it gets us the 7, which is what's actually there. 1, 2, 3, 4, 5, 6, 7. And then we have our disjoint sets. And so those are sets that do not have any elements in common. So if I'm using my example of 1, 2, 3, and N, which is 8 and 9, they have nothing in common. So if I union those two, M union N, I include everything that's in M and everything that's in N. So 1, 2, 3, 8 to 9. If I do the intersection of a disjoint set, so that's everything that's in M, but also in N, they have nothing in common, so there's no element that I can write here, so it's just the empty set. Reminder, it can either be the squiggly brackets with nothing in between, or I can do the 0 with the slash down the middle, which is also the empty set. And so if I do the number of elements that are in M intersect N, or the intersection of M and N, it works out to be 0 because it's the 0. There's an empty set, there's nothing there. If I do the numbers of M union N, or the union of M and N, I just add everything that's in M and everything that's in N. Because they have nothing in common, there's no overlap, I don't have to worry about minusing anything in this one. I just add what's in M and what's in N. So in this case, we have 3 for M plus 2 for, 2 for N. So there's 5 elements altogether. It's only when you have the overlap, like the previous example here, where you have to minus the piece. So for example, if you draw a card at random from a standard deck of cards, you'll draw a card from one of the suits, so either clubs, C, spades, S, hearts, H, or diamonds, D. So we have our picture here just to help. So we're going to describe each set in words, including the universal set U for this situation. So we have C. So what C is drawing a club. D would be drawing a diamond. And our universal set would be drawing any card from a deck of 52. Just a note, I am saying that this is a 52 card deck and we'll apply that later. So I'm not worrying about jokers or anything like that. If I wanted to include jokers, I would add that into my terminology for the universal set, but we're not doing that. Okay, so the next part, now we need the number of clubs. So the number in C. So the number of clubs in a deck is 13. Which number of spades is also 13. Number of hearts is also 13, and the number of diamonds is also 13. For the universal set, so the number in the universal set was the 52, because we're having 52 pack of cards. Now, if we wanted to do the number of S union H, or the number for the union of S and H, so that's everything in S, and that is everything in H. So there's 13 in S, there's 13 in H, so we have 13 altogether. Let's try that again. 13 plus 13 is 26. And for the next one, we have the number in the intersection of S and H. So that one is including the numbers that would be found in, or the cards that are found in spades and in hearts. And in this case, there's no overlap. You cannot have a card that's in the suit of spades and a card that's in the suit of hearts. So this one is the empty set. There's nothing that they have in common. So are sets S and H mutually exclusive? Are they disjoints? So yes, they are mutually exclusive because they have nothing in common. You can't draw a card and have it come for hearts and for spades, or count for hearts and spades. So yes, they're mutually exclusive. They can't happen at the same time. And if they're mutually exclusive, that means their sets have nothing in common. Which means they're also disjointed. Yes, mutually exclusive and disjoint. And then for describing the complement of S union H, and so the complement then would be the other two sets. So how I'm going to write that is S union H. So I want the complement of that. So that's everything that's not found in S and in H, which would be the other two sets, which is C and D. So that would be the union of clubs and diamonds.